Welcome back to AI from Zero to Researcher. In episode 1, we defined the core vocabulary, models as parameterized functions, learning as parameter adjustment, and the training loop that finds the bottom of the loss landscape. Today, episode 2, we give those ideas geometry. We'll see what parameters look like in space, meet the artificial neuron, and discover a pattern that no single straight line can solve. If parameterized function or loss landscape from episode 1 feel unclear, revisit that episode first. Today builds directly on those definitions. Here's a simple question. Can you draw a line that separates the gold dots from the violet dots? For this data, yes. One straight line, perfect separation. Now, what about this? Gold in the top left and bottom right, violet in the top right and bottom left. Try drawing a single straight line that separates them. You can't. No matter where you put it, one straight line will always get at least 1 point wrong. This isn't a trick, it's a fundamental limitation. And it's the most important failure in this episode, because understanding why a line fails here is what makes episode 3 make sense. But first, let's understand why lines are powerful, how they work mathematically, and what an artificial neuron actually is. In episode 1, we defined a model as a parameterized function from inputs to outputs. We trained the simplest model, one parameter, one multiplication. Today, we add more parameters, more inputs, and a crucial new ingredient, the activation function. If parameter or training feel vague, go back to episode 1 first. In episode 1, our model had one input and one parameter. Real problems have many inputs. Each input is called a feature, a measurable property of the thing we're looking at. A house has floor area, number of rooms, age. An email has word counts, sender reputation, number of links. A linear model assigns a weight to each feature. Multiply each feature by its weight, add them all up, and add a constant called the bias. This weighted sum is the output. The weight tells the model how much each feature matters. A large positive weight means this feature pushes the prediction up. A negative weight means this feature pushes it down. The bias shifts the output even when all features are 0. When the output is a continuous number, a price, a temperature, a score, this is linear regression. In 2 dimensions, it's a line. In 3 dimensions, it's a plane. In higher dimensions, it's a hyperplane. The model finds the weights and bias that make the surface fit the data as closely as possible. Each point has a vertical distance to the line. That's the error for that point. Training adjusts the weights to make these errors small overall. This is exactly the same idea from episode 1, just with more parameters. Now the more interesting case, classification. Instead of predicting a number, we want to decide which category something belongs to. Spam or not spam, cat or dog, or healthy. A linear model draws a decision boundary, a straight line or hyperplane in higher dimensions that divides the space into regions. Everything on one side is predicted as class A, everything on the other side is class B. The position and angle of the line are determined by the weights and bias. Different weights, different line, different predictions. But there's a problem. The raw weighted sum can be any number, negative infinity to positive infinity. For classification, we want a probability between 0 and 1. So we pass the weighted sum through a sigmoid function. The sigmoid squashes everything into 0 and 1. Large positive values become probabilities near 1, confident it's class A. Large negative values become probabilities near 0, confident it's class B. And right in the middle, at the crossover point, the model is uncertain. This is called logistic regression. Despite the name, it's used for classification, and its structure is about to look very familiar. Here's the artificial neuron. Watch it build, one piece at a time. Step 1. Compute the weighted sum plus bias. We'll call this Z. Z equals W1x1 plus W2x2 plus W3x3 plus B. Or, more compactly, using vectors, Z equals W dot x plus B. That dot means dot product. Multiply corresponding elements, add them up. Same operation, cleaner notation. Let's plug in real numbers. The inputs, weights, and bias are all shown on screen. Watch the weighted sum build. Each input gets multiplied by its weight, and the products are added together with the bias. Some contributions push the total positive, others push it negative. The weights decide which inputs matter most. The weighted sum comes out to negative 1.2. A negative Z means the neuron leans toward no. Now pass it through the sigmoid and we get 0.23, a 23% probability. One forward pass, concrete numbers, no mystery. Step 2. Pass Z through an activation function. A equals sigma of Z. If sigma is the sigmoid, we get logistic regression. But sigma can be other functions too. We'll meet ReLU in episode 3, which simply outputs max of 0 and Z. Notice, a single neuron with a sigmoid activation is logistic regression. They're the same computation. The neuron isn't a mysterious biological entity. It's a weighted sum, a bias, and a nonlinear function. 3 pieces. Right, that's it. The biological analogy can help you remember the structure. Inputs come in, get weighted, the neuron fires or doesn't. But don't push it too far. Real neurons are vastly more complex. The artificial version is a clean mathematical unit, and that's all we need it to be. Let's build this in code. First, a linear decision boundary. Now the neuron. Just one function. 3 lines. That's the entire artificial neuron. One neuron, one straight boundary. Change the weights, the line rotates. Change the bias, the line shifts. That's all a single neuron can do. Draw one straight cut through the space. Now let's hit the wall. Remember the pattern from the hook. Gold in opposite corners, violet in opposite corners. Let's try every possible line. 5%. 1 point is always wrong. No single line, no matter the weights, can separate this pattern. This isn't a failure of training, it's a mathematical impossibility for a linear boundary. To solve XOR, you need a curved boundary. And to get curves, you need to combine multiple neurons, each one drawing its own line, then mixing those lines together through nonlinear activations. That's exactly what episode 3 is about. And it's the birth of neural networks. Here's what we built today. Features are numerical descriptions of input. A weighted sum multiplies each feature by a weight and adds a bias. For regression, this directly produces a prediction. For classification, we pass it through an activation function like the sigmoid to get a probability. That full pipeline, weighted sum plus bias plus activation, is the artificial neuron. One neuron draws one straight decision boundary. That's powerful when the problem is approximately linear. It's useless when the problem is XOR shaped, when the classes are tangled in a way no single line can separate. The neuron isn't magic. It's a parameterized function with a geometric interpretation. In episode 3, we stack neurons into layers and add the crucial ingredient: nonlinear activations between layers. we'll see that a hidden layer literally reshapes the space so that XOR-like patterns become linearly separable. The network learns its own coordinate system. But this is called representation learning, and it's the idea that makes deep learning fundamentally different from classical machine learning. Instead of you designing features, the network discovers them. And here's the question to carry forward. We just saw that one neuron, one line. What kind of shape do you get from 10 neurons? 100? A million? The answer is almost anything. And that power comes with its own dangers, which we'll also address.